In this video, I'll be talking about relationship between the electric potential and the electric field. In the first lecture, I already talked about the relationship. What is the relationship between electric field and the electric potential? So V is the electric potential. Electric potential. E is the electric field. So if we know either of them, V or E, we can find the other. So the way we find out the electric field is how the potential changes with respect to the distance is the electric field. Okay, so the E is just the first derivative of the potential. If we know the electric field, we can also calculate the electric potential just by doing the integration. If we do the integration E dot dr, this is the scalar product, the dot product, then we can also find out the electric potential. And just to remind you, the dot product E dot dr, this is the dot product. The way it is defined is E dr times cosine theta, where theta is the angle between electric field and the position vector. So let's give you an example here. Okay, and also if the electric field is in the three-dimensional, then just let's say, for example, point charge. Due to the point charge, the electric field varies in all possible direction in three dimension into the space. Then the electric field in any direction, let's say along the x-axis, can be found out by taking the partial derivative of potential with respect to the distance. The first term here gives you the partial derivative of potential along x direction. I stands for the unit vector along the x direction. The same thing, if you need to find out how does the electric field change in the y direction, then you need to do the partial derivative of potential along the y with respect to y. The same thing, if you need to find out the electric field along the j direction, then you need to take have to do the partial derivative of potential with respect to g. That gives you the electric field along g direction. Now let's say you know the electric field. Let's say, for example, this is a parallel plate. This is an infinitely long plate, and due to the infinitely long plate, the electric field is given by E is equal to sigma over 2 epsilon naught. This is a parallel plate, charged parallel plate. Let me write down here. Charged parallel. I need probably more space here. This is a charged plate, and this is a point charge. Due to the charged plate, the electric field is given by sigma over 2 epsilon naught. That means it is independent of the distance. It does not change with the distance. So we know the electric field vector now. How do you find out the electric potential? You're going to use this formula here. The electric potential is the E dot dr. That's what it is. And at any point, if you look the electric field, this is the direction of the electric field, and the distance is also along this direction. Okay, and along y, if I just take any cross section along the y direction, it will be 0, because it doesn't matter whether you measure this point, this point, this point, or this point. There is no variation of electric field along this direction, along the y direction. So along the y direction, the electric field is 0. So at any point if I measure, so this will be the equipotential surface. There is no variation of electric field along this direction. The electric field is only along the x direction. So you have only one component of electric field. There is no component of electric field along y direction. If this is x direction, then the electric field is only along x direction. You won't get electric field along y direction. You won't get electric field along j direction. Only along the x direction. And how do you calculate it? So the electric field is a constant quantity, so I'm just taking this one out, and this will be simply equal to dr. Or if this is probably x, if I consider this axis as an x-axis, then I can simply write down as an x. So at any point, the electric field is given by E times x, or minus sigma over 2 epsilon naught times x vector. So what you see here, the potential is dependent on the distance. The further you go, the potential changes, but the electric field vector does not change. Now the same thing for the electric field due to a point charge is given by this equation. Now let's calculate the potential. The potential, the formula for calculating the potential is E dot dr. And here K, this can be given by K, Q, and the electric field is always along the radial direction, along the R direction. So the angle between the electric field and the position vector is 0 because both point in the same direction. So what I can write down is kq over r squared times simply dr. Kq is a constant, so 1 over r squared dr. Now let's do minus kq. If I do the integration, it will be r minus 2 plus 1 divided by minus 2 plus 1. And after further simplification, what I will get is kq over r. So we have now calculated the potential due to a point charge at A, if we know the electric field. So this is the formula for calculating the potential due to a point charge if you know the electric field. Okay.